So we've talked about all the different observations associated with gases. Pressure and volume are inversely related. We know that pressure and temperature are directly related, and all the other relationships that are expressed in the ideal gas equation. Now the question is, why do we see those relationships? And in order to explain that, we are going to need a theory or a model of gases. And the model of gases that was developed after 200-300 years of studies of gases is called the Kinetic Molecular Theory of gases. The main ideas are illustrated here, and the first one is that a gas is just a large number of very, very small particles, but kind of like billiard balls. They're always moving non-stop in random straight line motion. You can see this in the simulation here. And the molecules of the gas are separated by great distances. So there's a lot of empty spaces between one molecule and another one. They're so small relative to the spaces between them that we imagine them to be point masses, which just means that they have mass, but they don't really have any volume. They're so small relative to the spaces between them. The way I think the best analogy I can think about this is if you imagine you live in a rural area where there's one house and the next house is maybe 10 miles away, then that's sort of the way we imagine gases, which is very different than an urban environment where you have a house and 10 feet next to you is another house, right? So it's more dense compared to the gas situation. So that's why we can ignore the volume of these gases, because they really don't add up to a sufficient fraction of the volume of the container. These molecules, of course, will hit one another from time to time, but because the space is so big, that doesn't happen too often. However, they do hit the container. And when they hit the container, that's when we count that as pressure, because remember, pressure is force per unit area. The other thing we assume is that these molecules are moving at sufficiently high speed that they don't really exert forces when they're nearby each other. Molecules, of course, are composed of positive and negative charges, protons, electrons, and these particles have electrostatic attraction to each other. However, if the speed of the particles are high enough, the electrostatic attraction is no longer significant. This is like if you have two magnets attracted to each other. If you slowly move one magnet close to the other magnet, quickly you'll see a attraction, and the two magnets would bond together, would be attracted to each other, right? Now, if you move them rather fast, one magnet and the other magnet would not have time to actually make that interaction. And of course, this depends also on the size of the magnet. The smaller magnet, the less interaction they're going to be able to exert. And so the gas particles, because they're small and they're moving relatively fast, there's really no forces that occur between them. And that's the assumption that we make about how they behave. And then lastly, these molecules, as they're moving, they exert a certain amount of kinetic energy, and that kinetic energy is what results in the temperature of the gases. You can use the kinetic molecular theory to connect to PV equals nRT to the macroscopic equation that represents the behavior of gases. In order to derive that relationship, first we need that idea of pressure being equal to force per unit area. So we're going to start with this, and we're going to think about what does it mean to have force and area in the case of a molecule that's traveling along in a container that's a rectangle box, for example, and it's just going left and right like that. So when it hits the wall, it's going to exert some kind of pressure, right? And so what we need to know is, well, how do we quantify that pressure? Well, first off, we need to know what speed the molecule has. So we're going to just call the speed U sub x. We use U here because we already have V for volume, so we don't want to confuse those two symbols. And then x here just means that because it's traveling in that left and right motion, which is the motion in the x-axis, x direction. So we're going to just use that symbol U sub x, which is speed in the x direction. And the pressure that the molecule exerts on the wall will depend on a couple of things. One is just how often does the molecule hit the wall per a certain amount of time. So how do we quantify the number of collisions or number of hits per second? That collision collision must depend on how fast the molecule is moving. So in other words, it's proportional to the speed of the molecule, and then how many of them there are in that same box. If there are a lot of fast moving molecules, then there's a lot of collisions every second. If there is very few molecules and they're moving very slowly, then there's very, very few collisions occurring per second. The collision frequencies should be proportional to the speed of the molecule times number of molecules per unit volume. We can write that equation like this. Collision frequency is proportional to speed, which is u sub x, times n, which is the number of molecules, over v, which is the volume of the container. The other thing that determines pressure is how much quantity of motion is transferred from the molecule to the wall. And this is measured as something called momentum. It's not quite energy, but it's in analogous terms. Sometimes it's easy to understand it that way, that when I run and hit somebody or a wall, how much am I transferring from myself to that other object, to the wall or to the other person? Well, momentum is measured by multiplying the mass of the object that's hitting times its speed. And so that's given right here. The quantity is usually called the impulse, and the impulse is proportional to mass times the speed in the x direction. So in other words, the pressure that we quantify as force per unit area is just going to be the impulse times the collision frequency. So in other words, this mux times the ux times n over v. So that's what we wrote down right here. And then we can combine some of the terms that are similar together, and then it becomes looking like this: n over v times m times speed square. Particles are all moving in the x direction. However, they are not all moving with the same speed, right? So if you want to express this in reality later on as some kind of an average quantity, you have to take an average of those speeds. So that's important to point out, that what you're taking here is not the square of the average speed, but what you're taking here is the average of the squared speed. So let me repeat that again. You're not taking the square of the average speed, but you're taking the average of the squared speed. That's because the expression, this is the expression for one particle. If you have another particle, another particle, another particle, what you're going to do is really add all of those and later on average them out. So you're going to add the squared speeds, and then you're going to average it by dividing by the number of particles involved in the observation that you're making. So let's say there are 5 particles. They have speeds shown here. You can calculate the average of the squared speed by first squaring all of these numbers and then adding them and then dividing by 5. So that's the average of the squared speed. And when you do that, you end up getting this number. So that's the squared speed that has been averaged. And then if we take a square root of this, that number is what we call the root mean square speed, or RMS speed. It's basically just the square root of that number. And that end up being 518. If on the other hand, we just take these 5 numbers, add them and then divide by 5, 512 is the average speed, but it doesn't really capture the actual speed that's going on with that collection of 5 particles. So the 518 is actually a better measure of the average energy of the particle that's moving around. So that's why we don't use this number, the average speed, but what we use is the root mean square speed. And the term root mean square really tells you how it's being calculated. You have to square the speed first, and then you have to take the mean, which is the average, and then afterwards you take the square root. So remember that those are the 3 steps I did to get to the 518 number. So once we have the expression of the squared speed, this is what the pressure is proportional to. It's proportional n over v m now times u squared, but then with a bar on top of it, which just means that it's the average of the squared speed. Last thing we need to think about is just the different directions that molecules can move in. Right now we're only analyzing the x direction, but it's clearly possible that the molecules are going to move also in the y direction as well as in the up and bottom, which is the z direction. So if you think about the 3 directions, there shouldn't be any preference for the particles to move in x, y, or z. So therefore we can say that u squared x and y and z should all equal to each other. Each of them should just be a third of the total speed squared and then averaged out. So as a result, we would replace the ux squared with the bar on it with just 1/3 u squared with a bar on it. So your equation that's here now becomes this. And now you have an equality instead of a proportionality, because now you've expressed this in terms of all the 3 dimensions instead of just x. This is your equation from the microscopic model of the kinetic molecular theory of gases. And now we're going to go back down here to look at how that equation can be related to PV equals nRT. We know PV equals nRT is an equation that we can use to model the behavior of gases, right? Now, from the microscopic model, we notice that P is equal to this quantity, 1/3 n over v m u squared. And from the macroscopic model, we know that P is equal to nRT over v. So what that implies is that this number, this expression right here, must equal also nRT over v. That means we can cancel out the v on both expression, and you should end up getting this 3RT equals Na times mu squared. Because I'm talking about 1 mole of a compound, I end up getting Avogadro's number here, which is Na. Now notice that when I multiply Na by the mass, m is the mass of one particle. If I multiply those two together, I get the mass of 1 mole of a particle, which is just the molar mass, right? M. So in other words, we can write 3RT equals molar mass times the average of the squared speed. If we solve for the speed, which is taking the square root of the speed, we end up getting 3RT over m and then square root. This is of course our root mean square speed that we talked about earlier, because it's the square root of the average speed that has been squared. That's really important expression that you want to remember. In this case, this is how you calculate your root mean square speed for a gas. One thing to note here is that when you're doing this calculation, the value of the gas constant you're going to use is not 0.0821, which is the one you would use for pressure volume work, but you're going to use this other number, 8.314 joules per mole Kelvin. How do we get this number? Well, it's really just using some dimensional analysis to convert this to units of energy, joules. Why energy? Because remember, we're talking about the kinetic energy of these gas particles that are moving. Joules is actually a unit that in the SI unit system is expressed as kilogram meter square per second square. And so that's why we do this conversion to take it from liter atmosphere to that unit, kilogram meter square per second square, and that ends up giving us 8.314 as the value. So a related concept here is the meaning of temperature. And we start with that expression that we derive from the microscopic picture of gas particles, which is PV equals 1/3 NaMu squared. And the expression for kinetic energy is half times mass times velocity squared. In this case, we can bring that expression into this equation if we were to make 1/3 the same as 2/3 times 1/2, right? So that would give us 1/3 again. But the reason why that's important is because then the 1/2 can be used to multiply with mu squared to give us just kinetic energy. So then our expression becomes RT equals to 2/3 Avogadro's number times the average kinetic energy. Okay, so EK here is the symbol for the average translational kinetic energy, which is just the kinetic energy used for particles moving back and forth. If we rearrange this equation to solve for the kinetic energy, we get EK equals to 3RT over 2 times Avogadro's number. This would be the kinetic energy you get for one particle because you're dividing it by Avogadro's number. If you consider it for 1 mole of the particle, then the Avogadro's number disappeared because 1 mole of particle is Avogadro's number of particle. And so the kinetic energy is just 3/2 RT. Okay, so here's a second equation you need to memorize or remember along with that URMS equation earlier. Okay, so I would say that if you don't necessarily understand the derivation of a lot of these formulas, it's really important to just memorize these two equations, the equation for the speed and the equation for the kinetic energy of the particles. What this equation is telling you is that the kinetic energy of particle is proportional to its temperature, because remember, R is a constant, right? So what's that say? That says that that quantity that we so far have measured as temperature, which is just how hot or how cold something is, what it's actually measuring in reality is the kinetic energy of a collection of a gas. So when we have a hot day, like like 85 degrees Fahrenheit. We're saying that the gases in air is moving at a faster speed, and therefore it's generating a lot more kinetic energy. If we're measuring it at a colder day, let's say at 50 degrees Fahrenheit, then these gases are moving at a slower speed. And so that's really an important idea that you want to be able to understand with respect to how temperature is being measured, and how temperature allows us to determine how fast or how slow particles are moving.